Hey, what is up? We are starting chapter 8 now, right? And we're going to talk about what's called a sampling distribution, right? So the idea here really isn't too bad, but trying to make sure we get all the right formulas down and everything like that could be the confusing part. But the idea behind a sampling distribution is this, right? Remember, a distribution tells you the values that you get from your experiment and how many times they occur. And if we did a little graph of this, like for instance, the normal distribution picture looks kind of like this thing, right? To where since this is kind of low and this one's kind of high, this one occurs more often than that score, okay? So if we're finding a distribution of a sample, well, it kind of goes a little bit like this, right? If this is my population and you and I are both doing a study, right, I might take one sample here, right? Let's call it sample 1. And in sample 1, I do the little legwork. I calculate the average is 40, and the standard deviation here is, how about 2? Right? And then you go out and you pull out a sample of your own. Let's call it sample 2. And you calculate these same things, right? So let's say you find your average is 43 and your standard deviation is 1.6. Right? Just because we talk to different people, we got different values. So your sample has different values than my sample. So what the sampling distribution does, it looks at every possible sample. It will then write down all these values like we just did. And then once they have those, they will just consider the distribution of how many times each of these samples had a certain average or certain deviation depending on what we happen to be measuring. Okay? So a sampling distribution looks at all possible samples, and by the way, let's say these samples have size n, right? So we're not pulling out different size samples. If I pull out a sample of size 50, you pull out a sample of size 50, okay? So for a sampling distribution, it looks at all samples of size n, right? And then within that sample, it'll record the average, or if you're looking at standard deviations, it'll record those, and then it'll tell you how many times each of those occurs, right? So again, a sampling distribution just tells you the distribution of the possible samples, okay? So let's look at some more terminology here. So normally, I said we could pull out any number. Normally we are looking at a sample mean, so we'll just kind of stick with that for a while. Right? So again, I've got this population, and if you remember for the population, the average of the population we usually denote with a mu, and the standard deviation of the population we denote with a sigma. Right? And then when I pull out a sample, right, remember for the sample, the average is indicated with an x bar, and the standard deviation is indicated with a lowercase s, like that. Okay. What we are usually interested in something like this is what's called the sampling distribution of the sample mean. Okay. So again, all that means is I'm going to look at, again, the sampling distribution. So I'm going to pull out all possible samples that I can, and what I'm going to record is the mean or the average of all those. Right? So what happens is we'll pull out sample 1, and then we'll pull out sample 2, and then we'll pull out sample 3, and then we'll pull out sample 4, right? And then we'll make our horizontal line, and we'll just mark here every single time one of these scores actually occurs, right? And that's what my sampling distribution is going to look like. Right? So again, we're taking every possible sample, recording the mean from each of those individual samples, and then we're just writing down where that sample or where that average, the sample mean, happened to occur. Right? And then this picture is my sampling distribution. And what we're going to do is we're going to start asking questions not about individuals anymore, but about samples. So before we might have said, what's the probability that one person will have an ACT bigger than 6? Right? Well, okay, maybe bigger than 26. 6 would be a little embarrassing. So what we'll ask now is, what's the probability I will pull out a sample of size 10 and the average in that sample will have, I don't know, an ACT score of 26 or something like that. All right, so as I mentioned earlier, when you pull out sample 1 and maybe I'll pull out sample 2, we sometimes get different values for those, right? So that means we have variance in our possible answers, right? So that's called sampling variability. Right? What that means is, again, variability. Yeah. What that means is just when you pull out different samples, you'll probably get different results. Right? Every now and then we might pull out a couple of different samples and luckily get the exact same average and exact same standard deviation, but that's probably not the case. Right? That's why the samples are called variable, right? Because those values can be different. Right? So we're going to look at, again, how varied these samples can be, right? And of course, when we think variability, we think variance, right? Or maybe even standard deviation, right? So what we're curious about for these samples might be, what's the average of every one of these samples? What's the standard deviation for all of these samples? We got to figure out some ways to actually calculate that. And we want to be able to do it in a fairly quick, easy way so we actually don't have to calculate every possible sample, because that could take forever, right? But here are a few things that we know already. All right, so for starters, let's assume that we have this population, and this population, we know that it is already normal with a mean of mu and a standard deviation of sigma. Right? So what that means is when I start pulling out samples from this particular population, right, in this case, since we're starting off with something that's normal, then I know that the sampling distribution is also going to be normal. All right, so again, if I start off with a population that's normal, when I start pulling out these samples, the sampling distribution is going to be normal as well. Okay? So back here to the population, this is when we can pull out one person at a time, and I could say, what's the probability that X is going to be bigger than 5 or something like that, right? So we would do something along those lines to get one answer at a time. The types of questions we'll ask here will be about the sample. So the question might look something like this: what's the probability that the sample has an average bigger than 5? So the way we'd write this down is, since we're talking about a sample average, right, instead of saying X, or an individual, is bigger than 5, we'd say X bar, which is the average of the sample. What's the probability that that thing is going to be bigger than 5? Right? So if we're going to answer questions about all these different samples, we have to know what's the distribution for the sample. Is it uniform? Is it normal? Is it binomial, exponential? There are tons of different examples it could be. But if we're starting off with a population that's normal, then I know that this question is going to have some type of a normal distribution to it, which means I can use those charts in the back. Okay? So if you remember, the idea behind a normal distribution is you have to report a mean and you have to report a standard deviation. Right? For the population, right, that has a normal distribution with a mean of mu and a standard deviation of sigma, remember the average is just mu, the standard deviation is just sigma. Okay? What is it for all of my samples in this sampling distribution? Right? So for the sampling distribution, it's also going to be a normal distribution. Right? We're starting off in the normal distribution, so when we pull out these samples, it'll also have the normal distribution. And some of these things make sense, right? If you took the average of every possible sample, then you'll get some of the big scores, some of the small scores. It'll actually wind up balancing each other out. And for this one, the average of the sampling distribution is actually going to be the exact same thing as the average of the population. Right? So over here, if I'm in a normal distribution with the average of 10, standard deviation of 2, then the average here in all of these samples is also going to be 10. Right? But as we're going to see in class, when we start dealing with samples, the variance actually goes down, and it goes down by a lot if you have a really big sample. Right? So in the population, the standard deviation is sigma. Right? For the samples, the standard deviation is just going to be sigma over the square root of n. Right? So let's do some examples to see what these might actually look like. Right? So again, let's assume that I'm in a normal distribution, and for individuals, right, for a population, the average is 50 and the standard deviation, how about, is 10. Okay? What I'm going to do is I'm going to make a sampling distribution, right? And I'm going to pull out samples of size 4. Right? So in the sampling distribution, since I'm starting off with the population being normal, it's also going to be normal. The average of the samples is going to be the exact same thing as the average of the individuals. That's going to be 50. But here's where we get a change. The standard deviation of the population is 10. The standard deviation for the samples is 10 over the square root of n. Right? So in this case, the sampling distribution is going to be normal with an average of 50 and a standard deviation of 10 over the square root of 4. Right? And of course, that's the same thing as 10 over 2, which means all of the samples have a normal distribution, an average of 50, and a standard deviation of 5. Right? That's if we have a sampling distribution or a sample of size 4. Right? What if I have a sample of size 16? What are all those samples going to look like? Well, since we started off in the normal distribution, we'll still be in the normal distribution. The average is still going to be the same, still going to be 50. But the standard deviation for the samples of size 16 is going to be the original standard deviation over the square root of 16. So in other words, this will be a normal distribution, average of 50, square root of 16 is 4. So it'll be a normal distribution, an average of 50, with a standard deviation of 2.5. Right? And I mentioned it before, but you can see here, as the sampling distribution gets bigger and bigger, the standard deviation starts to go down. Right? And the reason for that is, instead of looking at one score at a time, we're looking at 4 scores or 16 scores. Okay? And now once I know this, I can answer a question along these lines, right? What's the probability a sample of size 16 will have an average, how about larger than 51? Okay. Well, what we have to do is look at our question and see what setting are we in. Right? So in this case, I'm looking at samples of size 16, which means I want to work with this case right here because that's my sampling distribution for samples of size 16. Right? So I will answer this question based on the normal distribution with an average of 50 and a standard deviation of 2.5. Right? So the picture would look like this, right? At least for the samples of size 16. The average is still at 50, and I want to find the probability of getting 51 or more. Okay? So what we do is we'd get our z-score, so it'd be 51 minus 50 over the standard deviation, and since I'm dealing with samples of standard deviation, I'll use that particular standard deviation of 2.5. Right? So this is 1 over 2.5, which is 10 over 29, 2 over, which is 0.4. Okay? And then if we look up 0.4 in our charts, we get 0.6554. Right? But remember, that's the area from here all the way back, right? So that's 0.6554, which means this is 1 minus 0.6554, which is 0.3446. Okay? So that's the probability that sample has an average larger than 51. Okay? So let's look at a few more examples here. What if I start off with something that's the normal distribution with an average of 100, standard deviation of 8? Right? What I'm going to do is I'm going to pull out samples of size 25. Okay? So this, again, is just for individual scores. Right? The question says this: what's the probability the sample of size 25 will have an average lower than 98? Right? So let's read the problem. We're talking about samples of size 25. Right? So we have to ask ourselves, what's the distribution for samples of size 25? Right? Well, again, for individuals, it's this. Right? For the samples of size 25, since we started off with the normal distribution, we'll still be in the normal distribution. Going to have the exact same average, but to get the standard deviation for all these samples, we'll take the old standard deviation and divide it by the square root of the sample size. Right? So it'll be normal, average of 100, and then square root of 25 is 5, which gives me an average of 100, and 1.6 is the standard deviation. Okay? So now we can answer the question about the sample since we now know what the distribution for all those samples looks like. Okay? So here we have our picture. The average is at 100. What's the probability in this sample I'll get 98 or lower? Well, let's find the z-score. I'll take my 98, subtract the average of all the samples, divide by the standard deviation of the samples. So it gives me negative 2 over 1.6, which gives me negative 1.25, right? And if you look at the charts to find that probability, right, if you look up negative 1.25, you get 0.1056. So from here on down, that's 0.1056, and that's the probability that we're looking for. So what is this probability? 0.1056, or a 10.56% chance. All right. So this rule that we are using, this is called, if you want to flip over to your book on page 373, this is called the central limit theorem. And it says this, right? It says that regardless of the population, so in other words, we can start with normal, or maybe we've started in the uniform, starting in the binomial, exponential, whatever, right? So we've got our population, and you know what? We may not even know where we're starting in, okay? But here's what the central limit theorem says. It says regardless of the underlying population, right? So again, the sampling distribution of x bar, all right, our sample mean, becomes approximately normal as the sample size increases, right? So if we start off with something that's already normal, then when we start pulling out our samples, it's automatically normal. But let's say I start off in the uniform distribution. All right, so again, here's my data, and I'm in the uniform distribution. Then if I pull out one sample and take its average, it's not necessarily going to be normal. But if I take out a sample of size 10, or a sample of size 20, or a sample of size 30, right? The bigger the sample sizes I take out, the closer it's going to be to the normal distribution. Right? And the general rule of thumb is this. When n, the sample size, is bigger than or equal to 30, then the sampling distribution, x bar, is always close enough to the normal distribution. Right? So again, if I start off with something that's already in the normal distribution, samples of size 1 are in the normal distribution. Right? If I start off in the uniform distribution, then samples of size 2 or 3 or 4 might not be enough. Right? Or if I'm in the exponential distribution, samples of size 5 or 6 might not be enough. But once I get to samples of size at least 30, then I know that I can always say the samples, right? So x bar, its distribution is going to be approximately normal with the mean of mu, whatever comes from the population, and the standard deviation of sigma over the square root of n. Right? This is what I can use to answer questions about my sample at any time, as long as I'm taking big samples. Right? So again, if I know I'm starting off with normal, I can use it any time. But if I don't know what my underlying population is, or I do know and it's not even close to being normal, then you can start taking out samples to see if they're going to be normal or not. And they will be once you get to samples of size 30. So let's look at this particular problem. Right? Let's say that we have some type of a population here. I don't know if it's normal, exponential, binomial. I don't know anything about it. I just got these numbers in front of me. Okay? But what I do know is I've done a little bit of number crunching, right? And I found that the average in this population is 36 and the standard deviation is 18. Right? And what I'm going to start doing is let's pull out samples of size 36. Right? So in this case, I'm going to say n equals 36. Right? So the first question is, what is the distribution for these samples of size 36? Right? Well, first thing we notice here is that n is bigger than or equal to 30, right? Since we are at 36, right? So that's good. So what that means is we can assume that these samples of size 36 are approximately the normal distribution. We know that the average of the samples is going to be the same as the average of the population. It's going to be 36. I know that the standard deviation of the samples is going to be the original standard deviation over the square root of n. So in this case, that's going to be 18 over the square root of 36, which is 18 over 6, which gives me 3. Right. So that means the samples have the normal distribution with an average of 36 and a standard deviation of 3. So now if I have a question about a sample, this is what I use, because that's the distribution for a sample. Okay? So if I said to you, what's my probability? Oh, I don't know. How about X bar is, I don't know. How about less than 30? Okay. Well, whenever you see X bar, that should be a hint that you're talking about the sampling distribution. Right? So it'll look something kind of like this. Right? So there's the average 36, there's 30, and I want to find the probability this sample is at 30 or less. So let's get our z-score. So it'll be 30 minus the average, and the standard deviation for the samples is 3. So it's minus 6 over 3, which gives me a minus 2. Okay. And if you look up negative 2 in your charts, you get 0.0228. Right? So that's its probability. All right, so again, the big thing here is, are we talking about populations one score at a time, or are we talking about samples, which could be 5, 10, 20, or 100 scores at a time? Right? If we are dealing with samples, then we have to understand what's the distribution for the sample. Using the central limit theorem, we can, as long as n is big enough, at least 30, we can always assume it's a normal distribution with that mean and standard deviation. Right? So in 8.1, let's start with these numbers. How about just look at 1 through 8. Those are some short answer questions for you. And then look at 9 and 11. Let's see, how about 14, 15, and then let's do some of these applications. Here's number 20. How about 21? And let's go with 27. And let's leave it there. All right. So hopefully it helped. We'll talk more about this stuff in class. Hope you guys have a good day. See you later.